So hey everyone, welcome to Homological Algebra. This lecture will be split into two parts. One part where I will outline the general language of homological algebra, which we will also use when we talk about algebraic topology or about the derived complex. And in the second part, we will go into some more algebraic applications of this and ultimately discuss derived functors and all that stuff surrounding those. And the general motivation is that sort of a lot of global properties of algebraic or geometric objects can be somehow described or encoded with, well, either a homology theory or a cohomology theory. And what cohomology theory or homology theory means is just a way of associating a sequence of groups or of modules to some object, either algebraic or geometric. And these groups are then called cohomology groups or homology groups. And we usually do this by means of an intermediate object called a cochain complex. And this is sort of the first kind of thing we're going to introduce here. Oh yeah, by the way, yeah, I should maybe elaborate on what I mean by global properties. So those properties are stuff like, well, either if I have some kind of topological space, then properties like, does it have holes? Can I contract every loop? Stuff like that. And when we're talking about groups or Lie algebras, it's more something like, I have some exact sequence, meaning that C is somehow isomorphic to some quotient of B over A. Then the question, does that mean that I can write B as some kind of product of A and C? Okay, so we're going to be talking about chain complexes and cochain complexes of modules. In theory, we can do this with any kind of abelian category, but never mind, I guess. So a chain complex of R modules is, well, consists of two things, namely a sequence indexed by the integers of R modules and a sequence d lowercase n, no, lowercase n, but like subscript n, of, yeah, again, indexed with the integers of R linear maps, where di goes from ci to ci minus 1, and they have one property such that when we compose two of them, that this is 0. We can write this as such a diagram. ci minus 1, di minus 1, dot, dot, dot. And yeah, there's a lot of terminology around all of this. So maybe I do this in a sort of different pen. We call CI or the elements of CI are the I chains. The map DI is called the ith boundary operator. Now the kernel of DI, i.e. the I chains that are mapped to 0 under the ith boundary operator, they are called the I cycles. And the image of DI minus 1, i.e. those I chains that are in the image or that are produced by the I minus first boundary operator are called the I boundaries. And this terminology makes a lot of sense if you're talking about the simplicial chain complex, as we will do in algebraic topology. At this stage in time, it's just names we give to the things. Question. Yes, the definition and intuition comes from algebraic topology, where we're talking about simplices, and then chains are like linear combinations of simplices. The boundary operator associates with each simplex the linear combination of the faces of that simplex. Cycles are linear combinations of simplices that have no boundary, and well, boundaries are boundaries. But yeah, at this point, it's just a name. Yeah, and the condition that this this composition of boundary operators is 0 just means every I boundary is also an I cycle. And in a way, we will later classify in how many ways I cycles can fail to be I boundaries. Oh, that's what the homology is all about, actually. Okay, and now we can also define the dual notion of this, namely a code chain complex. And is a chain complex in the opposite category. Probably not that helpful. Consists of, well, we have R modules, and we have again R linear maps, now with their index as a superscript. Linear from DI goes from CI to CI plus 1. And again, the composition of two of these operators is also 0. And yeah, we can write it again like this. And so on. And well, when it comes to nomenclature, I don't know, people are not very creative. So what do we have? The elements of CI are called I cochains. The operator DI is the ith co-boundary operator, the kernel of di consists of I cocycles, and the image of di minus 1 consists of I co-boundaries.
So basically the difference between the two is just the indices and the maps going from the greater to the lower index, the other way around.
Yeah, in a way. The way it's usually done is that you say that everything is just indexed by n naught and not z. And then the difference is that a chain complex finishes at some point and a cochain complex starts at some point. That's at least how I remember this stuff. Yeah, for those among us who did topology in physics last semester, the de Rham complex is a cochain complex, where di is just the exterior derivative, or the exterior differential. And then like cochains are differential forms, I cocycles are closed forms, and I co-boundaries are exact forms. But I guess I will expand on that when we talk about the de Rham complex.
Hey Philip, so I have a question. So like let's talk, like if we're talking about the topology in physics example you were giving, so over there CIs were the chains, and like C subscript I were chains and C like superscript were cochains, right?
Yeah.
And apparently you said some opposite category stuff, right?
Yeah.
And how does the chains become cochains, or is it just like a name to,
like there's no map from some category to its opposite category.
okay, so these two are totally independent.
They are completely independent notion. The only reason why I said the opposite category is because you get, basically, if you have this picture of a cochain complex and you just reverse every arrow, and then you get this picture for a chain complex.
Okay, but like over there also, like in the there's a mapping between like the de Rham cohomology and the like normal homology, right? Like some
Yes, that is the Pontryagin duality. Yeah, this, I think that's what it's called.
Yeah, and so why is that happening? Like if they are two independent notions?
Oh, that is they are a priori independent of each other. The fact that they are not is like a deep theorem, okay. But it's like only very specific cohomology theory and a specific homology theory that have this dual pairing.
Okay. Yep.
It's not like a general thing.
That sounds good. Thanks.
Okay. And now to sort of keep in theme with my category lecture, I've given you a new kind of objects. So what are the morphisms? And the morphisms, well, are called chain maps. F between two chain complexes. C and DC, and D and DD is a sequence of module map or of linear maps. Fn of our linear maps. Such that, well, if we look at this diagram, DCI, CI minus 1, and the one for the chain complex D. And we have those maps between them. So Fi goes from Ci to Di, by the way. Fi, and we have here Fi minus 1, then they commute. This diagram commutes. In other words, we have Di after Fi is the same as Fi minus 1 after Dic. So yeah, it's a structure preserving maps. It's a map such that these boundary operators play nicely with them. And similarly, we can define a cochain map, which is the same thing for cochain complexes. And well, it shouldn't surprise you that chain complexes and cochain complexes, together with their respective chain maps, form categories. And okay. Now the definitions don't really stop, but I guess this was sort of to be expected. So what these, well, okay. So if we have a cochain complex or a chain complex, and we call it exact, if, well, basically, if we look at this picture, then this, what we see, should just be an exact sequence. Written out, this means we have that the image of Di is equal to the kernel of Di minus 1, or respectively, a similar thing for the co-boundary operator if it's a cochain complex. And well, this relates to our definition, or let's say by definition, we already have that this is a subset. And if it happens to be the whole kernel, then we call this complex exact. Same here. And we can now measure how much a complex fails to be exact by defining the homology and the cohomology groups for a chain complex. Define define the ith homology group HIC to be the quotient of those two things. We are talking about modules, so we can just take quotients, and they are again modules. Since in algebraic topology, people are usually interested in the case where our ring is just Z. So we are not talking about some weird modules, we're just talking about abelian groups. So then these quotients are also just abelian groups, and we call them homology groups. And therefore this terminology is also used here, even though they are, I guess, more than just groups. Of C. And similarly, for a cochain complex, define H superscript C to be, well, similar thing, kernel of D superscript I divided by the image of, well, D superscript I minus 1, called the ith cohomology group. Of C. And yeah, as I've already said, they sort of measure to what extent our chain complex or cochain complex is not exact. Or in other words, HI concretely measures how much I cycles or co-cycles fail to be or are I boundaries or co-boundaries. And yeah, I guess what is an interesting property is that they actually form functors, this homology group or cohomology group. So I guess first thing to note, chain complexes and cochain complexes form a category together with their respective maps called CHR or co-CHR. And we have
Co-CH is not the same as CH-op? Probably not.
No, I don't think so. Yeah, and I guess the main statement is that every HI is a functor from CHR to R mod. And H upstairs I is also a functor. Note that I didn't use any kind of opposite here. Or in other words, if we have a chain map, this map also induces linear maps on all of the homology groups in such a way that they behave nicely under composition. And I guess, yeah, I'm not really going to prove everything, but like just show you how they are defined. So if we have F, a chain map from C to D, then define HI of F, well, it's a map from HI of C to HI of D. What is this? It is the kernel of DI divided by the image of DI minus 1. C, and here. So what shall we do? We take an element, oh wait, plus 1. Okay, happens all the time. And we just map it to fi of x plus im di plus 1 d. And this is well defined because we have a chain map. So our fi behaves nicely with respect to these boundary operators. And yeah, everything is just a whole lot of diagram chasing. Not going to do that here. Now for yet another definition. This sort of ties in to the part in the category theory lecture where we had categories and then functors, and then we're like, oh wait, we can also define something between two functors. We're now defining chain homotopies. Let CD be chain complexes and F and G from C to D be chain maps. The chain homotopy H between F and G is given by a sequence again. HI of our linear maps such that every HI goes from CI to DI plus 1. And we want such that HI minus 1 after DIC plus DI plus 1D after HI is equal to FI minus GI. So the general idea of this concept is that we have, well, our two chain complexes, CI minus 1 and DI plus 1, DI minus 1. And we have FI plus 1 and GI plus 1. Yeah, all of them going downwards. And then we have those maps that go diagonally. And we want those maps to sort of be intertwined with all of those boundary operators, such that when we go along this path versus we go along this path, that the sum should be the difference of those two things here. Really weird concept. At face value, it doesn't really make any sense. But the nice thing is that in some very perverse sense, you can get this by from a homotopy between two continuous maps of topological spaces when you're considering the respective homology theory of topological spaces. So again, a notion induced by geometry or by topology, and then just carried over for all of those things. And yeah, dually, we can again define a co-chain homotopy. Or the notion of a co-chain homotopy. And I guess, yeah, now we can, when we have some notion of homology, homotopy, wait, did I call it? Yeah, homotopy. we can sort of define the usual notions of what it means to be homotopic and what it means to be homotopy equivalent, namely two cochain maps or chain maps, F and G from C to D are called homotopic. Symbol is this. If there exists a homotopy between them, and by the way, I'm going to abbreviate homotopy by H-topy and homology by H-logy. And similarly, two co-chain complexes, C, D, are called homotopy equivalent. If if there are cochain maps or chain maps, F from C to D and G from D to C, such that F after G is homotopic to the identity on D, and G after F is homotopic to the identity on C. Sort of in analogy to topology, where we have the same notions. And I guess the question is, why would, firstly, homotopies or homotopic maps, why would that notion be interesting? And why do we even consider it? And secondly, the same about homotopy equivalence. And the reason is that homotopic cochain maps induce the same map on cohomology or homology. Or in other words, if F is homotopic to G, then HIF is equal to HI of G. Or the same thing with the upstairs indices. And I guess you can see it coming if the complexes of two complexes are homotopy equivalent. They have isomorphic cohomology or homology groups. Just because the HI are a functor, so then when you have a map from C to D and from D to C, you have maps from HIC to HID and back. But then the composition is just HI of one composition or of the other composition, where those things are homotopic to the identity. So then the HI applied to that should be the same as HI applied to the identity. But again, since that's a functor, it's just the identity. And this way you prove isomorphism. I don't know, should I elaborate on that? Okay. And lastly, there's one very important tool when you're dealing with chain complexes or cochain complexes, and that one comes in the form of theorem/definition, which is always the best kind of thing, best kind of heading. We have a short exact sequence of chain complexes. Just meaning that we sort of have chain maps between A and B and between B and C, such that on every level it's a short exact sequence. Formally, it's like the same because chain complexes and co-chain complexes then form an abelian category, and in every abelian category you can talk about short exact sequences. Whatever. Then we have an exact sequence of the homology groups. Namely, we have hi of A, then hi of B, then hi of C, and then we go one level below. A, hi minus 1, B, hi minus 1, C, hi minus 2, and so on. Jesus. And this sequence is called the long exact sequence. Or abbreviated LES, or associated to that short exact sequence. Yeah, if we're dealing with a particular homology theory, then I don't know, a lot of these short exact sequences come about naturally, and then you can write down the long exact sequence for that. And usually some of these things happen to be 0. And then everything just gets much simpler because, I don't know, then maybe you get isomorphisms or something like that. So that's just a useful tool for computing these homology groups. I guess you will have to believe me. In algebraic topology, I guess we will do an example of how to compute all of the homology groups of the spheres. But I guess that will have to wait. And yeah, if we just replace the word chain with cochain, then we also get a long exact sequence. Only that now it has a somewhat different it's basically snake lemma on steroids. Or one could also say the snake lemma is some weird special case of this. Well, in any case, for cochain complexes, the sequence looks slightly different because, well, essentially we are not going 1 degree down, but 1 degree up. So we have HIA to HIB to HIC, and then we go to HI plus 1, A, and so on. And yeah, again, the people who did topology in physics last semester, the Meyer-Vietoris sequence is exactly an example of such a long exact sequence. And I guess that was the language part of today. So now for the second part. So when we're looking at these, if we want to generate chain complexes or co-chain complexes, we usually generate them by means of an injective or a projective resolution. And well, they very much involve choices, but it turns out that for different choices of an injective or a projective resolution, we get homotopy equivalent co-chain complexes or chain complexes, and therefore the homotopy, the homology groups or the cohomology groups don't really care which resolution we chose. Okay, but I guess we will first start by saying what is an injective or projective resolution. P, and our module P is called projective. If sort of we can extend along module epimorphisms if any are linear map whose domain is P, can be lifted along, well, module epimorphisms or like surjective are linear maps. In diagram, we have any kind of R-linear map from P into another module M, and we have surjective map from N to M, and this property of projectivity means that there exists a lift. Not a unique one, but just any one. Similarly, an R module Q is called injective if any module homomorph, or if any R-linear map whose codomain is Q can be lifted or can be extended. It's Q. Along injective linear maps. In diagrams, we have our module Q, maybe a bit lower. And we have any kind of R-linear map from M into that thing. And then we have an injection from M into N. And we can extend this R-linear map. And, well, I guess you could again say a module is injective if it's projective in the opposite category, and vice versa, which, yeah, is sort of something that we should keep in mind. And yeah, sort of the big theorem is that the category, okay, maybe another comment, this notion very much extends to objects in any kind of abelian category, I believe. You then talk about projective and injective objects. And yeah, sort of a pertinent question is always, are there enough of them? So we say the category of R modules has enough injectives and projectives. This is actually a statement that has a rigorous meaning, namely, i.e., for every R module M, there exist a projective module N such that, well, we have a surjection from N to M and an injective module N prime such that, well, we can inject M into N prime. Examples of projective or injective modules. So the thing is, injective modules are very, very stupid to work with. So people usually avoid it. Usually so I guess we can give a constructive proof for the thing with projectives. Slash example is the following. Every free module is projective. What does free mean? Free means we can write it as some power of R, or like some direct sum indexed by some set of copies of R. It's projective. And well, how do we build such a surjection? We know that any kind of module always has a generating set. Let M be generated by, well, some objects X alpha for alpha in some set. Generated just means that we can write every X as some linear combination over R. And then we can define the map. The map R to the, well, I in brackets to M. That maps some vector of coefficients is mapped to that linear combination. Xi, I suppose. Where very importantly, only finitely many AI are non-zero, so that we always have finite sums because this is algebra and we have no notion of convergence. And because the set of Xi that we chose was a generating set, this is surjective. So yeah, we are done.
The small sequence in the top, two lines above, is exact, isn't it?
Yes.
Okay.
I.e. in this case, N to M is surjective and M to N prime is injective. Yeah, that's generally, for injective stuff, it's a lot harder, but it's also true. Okay, now what we now want to define, or what we want to work towards, is the notion of the derivative of a functor. And well, for that, we first need to generally look at how functors behave with respect to exact sequences. So if we have a functor from the category of R modules to the category of R modules, or I guess generally between 2 abelian categories, and we have a short exact sequence, then this sequence is again mapped to like some sequence of maps by this functor, but we don't know if it is exact again. And well, if it is in some way, then this is a special property for the functor. So this is what we're defining, is called left exact. If for every short exact sequence 0a b c, sequence 0 to fa to fb to fc is exact. Notice that we don't have anything here. So what this basically means is that sort of injective maps are again mapped to injective maps, but not necessarily for surjective maps. And we still have some preservation of images equal to kernel. Conversely, we call it right exact. If, well, again, for the same kind of sequence, for the same short exact sequence, the sequence fa to fb to fc to 0 is exact. So the notion of surjectivity is preserved, but not necessarily the notion of injectivity. And we call it exact if, well, it is both left exact and right exact, or conversely, if we just get a short exact sequence at the end. If blah, 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 0 to fa to fb to fc to 0 is exact. Oh, yeah, something else I forgot over all of the proving and call for examples of our theorem that there are enough injectives and projectives. The statement that there are enough of them is basically equivalent to saying that there are injective and projective resolutions, because we can sort of apply that statement recursively, and then we get that there are exact sequences R2, R1, R0 to M to 0, and conversely 0 to M to I0 to I1 to I2 ... exact, where the Ri are projective and the I are injective. And just by looking at this, this already looks a bit like, well, we have something that stops, and we have sort of decreasing indices, and we have something that starts, and we have sort of increasing indices. And I guess I've already written the indices in a sort of suggestive manner, but this is eventually where we are going to get a chain complex or a cochain complex from. Now for our definition / theorem of derivatives of functors. So let M be a module and R module, and let F be a right exact functor. Then we can choose some projective resolution of M. P2, P1, P0, and 0 be a projective resolution. Then we can apply our right exact functor to that. And well, the thing is, this thing here is an exact sequence. If we apply our right exact functor to it, we don't know, or like it's probably not going to be an exact sequence anymore, but it is going to be a chain complex. And this is exactly because F is right exact. Then Fp2 to Fp1 to Fp0 to, well, we can just stop after P0, forget about M essentially, and then just map to 0. This is a chain complex. And well, we can then take homology groups. Define LIF of M to be the ith homology group of this complex. And now, yeah, this is sort of, I guess the notation already says that we are again trying to define some kind of functor. So we've here said what it does with objects. What does it do to chain maps or to modular homomorphisms? And this is sort of where the projectivity comes into play. If we now have a module homomorphism, F from M to N.
F of P dot is just the notation of the complex.
Yes. Yeah, people are usually a bit ambivalent of if they want to write a dot there or not. In this case, I did it. Just a notation. So such a module homomorphism lifts to a chain map. Of, well, basically, yeah, notation is hard. If we denote the projective resolutions of M and N by PM and PN, then to chain map between these two complexes. which then lifts to unique morphism between LIF M and LIF N. And well, we're going to call this one LIF F. And yeah, this is all very tedious, but in essence, we can prove that firstly, this is sort of well-defined. Like if you use a different resolution, then in the end, you're going to get homotopic chain complexes here. Homotopic chain complexes, which have isomorphic homology groups. So the action on modules, on objects is already sort of well-defined. And similarly, this map here could lift in different ways to different chain maps, but those are homotopic. And then you get, if you then apply the homotopy group functor to it, you get equal maps between those homology groups. And then we can prove that this obeys all of the nice functor laws. The upshot being that LIF is a functor called the ith left derivative of f. And it is apparently not very hard to check that L naught f is the same as f, which I guess makes sense if you derive, if you take zero derivatives, or if you derive 0 times, you shouldn't change the thing. Yeah. So note, we started with a right exact functor, and then we're sort of able to classify how much it fails to be left exact. And we do this by looking at the ith left derivative of f. And similarly, dual notion, well, let f, again, m be a module and f left exact. Then we can choose blah, 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 an injective resolution. I0 to I1 to and so on. Injective resolution. Then we can apply f to that thing. Again, scrap the first object. 0 to f of I0 to f of I1 to f of I2 and so on. The fact that our functor is left exact means that while this thing here isn't necessarily an exact sequence, it's a cochain complex. And then we can take the cohomology groups. And we call this one RIF of M is then the ith cohomology group of the cochain complex Fi upper dot. And yeah, this way we define what's called the right derivative, the ith right derivative of f. And again, we have the 0th right derivative is f itself. So again, we have a left exact functor that doesn't necessarily have to be right exact. And we take whatever injective resolution, cohomology, whatever, and then we get the right derivative that measures how much this functor fails to be right exact. And the upshot of all of this is that we have a...
What exactly does RIF do on the morphisms again?
Okay, you have a morphism on modules, and this one lifts to a morphism to a code chain map because it's an injective resolution, and injectivity sort of implies that we can do that. Would have to look a bit more into that to give you the to write it down explicitly. And yeah, that code chain map, then you apply the cohomology, and yeah. Yeah, I guess the upshot of all of this is that the chain complex and the code chain complex, I guess, that we constructed has a very interesting long exact sequence. So if f is left exact, and 0 to A to B to C to 0 is a short exact sequence of modules, then we know that the sequence 0 to FA to FB to FC to 0, that this thing isn't necessarily exact. We know that if we exclude this thing at the end, then it is exact. But what if we actually want to carry on? So the long exact sequence does exactly that. It says, okay, we have here the 0th cohomology groups of that, sorry, left exact, right derivatives, code chain. Okay. We have the 0th cohomology groups here, and then we can just, well, the long exact sequence says, okay, then we take the first cohomology groups, R1FB to R1FC to R2FA, and so on. Well, and this now tells you exactly how our right derivatives tell you how much this functor fails to be exact. Namely, if the first right derivative of f applied to A happens to be R1FA, if this just happens to be 0, could be, then we have a 0 here. So then FA, FB, FC 0 is indeed exact.
So this long sequence is always exact.
Yes. It's exact. Yeah, sorry, I sometimes say stuff which I don't write down, but yeah, the long exact sequence is exact. Yeah, I guess conversely, if f is right exact, then, well, we can sort of extend to the left. L1F A, L1F B, L1F C to FA to FB to fc to 0, which is exact. So again, if L1 fc happens to be 0, then, well, for this particular choice of A, B, and C, we indeed have, again, our exact sequence, our short exact sequence that we wanted. So, yeah, this is all very abstract, I guess. No shit. Yeah, a nice example would be in order, I think. So one of our favorite functors, we now meaning the guys who already took commutative algebra, is the functor that takes a tensor product. That's A and B are modules. Then the functor where we just take a tensor product with B is right exact. Because if we have a surjective map, well, we can find the surjective map of the tensor products with B, but injectivity might fail because we could have some torsion. So this functor is right exact, so we can left differentiate it. I don't actually know if it's called left differentiate or left derive. I don't really care. We define Tor IR of A and B to be the left derivative, the ith left derivative of the functor tensor product with B applied to the module A. Do I have some interesting examples? No, I actually don't. So this functor, the Tor functor, is sort of important. It pops up in the universal coefficients theorem in algebraic topology, which tells you how to relate singular homology groups for different coefficients or for different coefficients groups to each other. But whatever. The main point is that it sort of measures the amount of torsion that occurs within B. But some properties are that, firstly, it is symmetric. So we can exchange B and A. Very importantly, if R is a commutative ring. Oh, Tor. Yeah. Apart from that, this is basically just, firstly, the fact that the tensor product is symmetric, and secondly, yeah, some weird zigzag lemma stuff that basically tells you how to work within a double complex. Weird stuff. And secondly, something how to deal with direct sums. A alpha B, and this again is more or less due to the fact that this all holds for the tensor product. So then by some weird argument. Yeah. And thirdly, the long exact sequence stuff. So if 0, A, B, C, 0 is exact, then, well, Tor 1, AM, Tor 1, BM, Jesus, Tor 1, CM, A tensor M, B tensor M, C tensor M, 0 is exact. So if C has no M, if M has no C torsion, no, if C has no M torsion, then this sequence, this shorter sequence is also exact.
This is exact for every M?
Yes.
Okay.
I feel like we should look at an example of this.
If we have a flat module, we know that the tensor product is left exact as well, or
Yes.
exact. We can therefore right differentiate it. Is there any reason behind this?
Well, I mean, the tensor product is right exact anyway. So all of, yeah, all non-zero right derivatives are just 0.
Okay.
Yeah, I guess we could work through a short example. So we want to look at Tor of Z and Z modulo n, of course. But I'm improvising at the moment. So do comment if I do make a mistake. So the great thing is that we are working with, so firstly, this thing is symmetric, so it doesn't really matter in which order we do this, or in particular, if we take tensoring with Z or tensoring with N, I think we need to do something like this to make it interesting. Well, okay, in this case, my comment doesn't really say much. So the great thing is we're working with modules, so we don't, we not only have projective resolutions, but we can just take a free resolution. In this case, we take a free resolution of Z modulo n. Well, this thing has one generator, namely 1. So we can just map, we can just take, well, essentially the quotient map. And then the kernel of this map is just nz. So we can take multiplication with n as a surjective map again. And then we just have 0. So this is our projective resolution, and it's even finite, nice. Then we can apply the tensor product with n to it, well, kicking out this one here. So then we have, well, if we take the tensor product of Z with Z modulo n over Z, we just get Z modulo n. And, well, again, Z modulo n and 0. And now the question is, what is this map here? And the thing is, this map is multiplication with n. So if we go to the quotient, this is the 0 map. What does that tell us? Well, so this is a chain complex. And then the zeroth homology group of this complex is just the kernel of this map modulo the kernel of this, the image of this map. So the kernel of the zero map is just z modulo n, and then we divide it by the image of the zero map, which is 0. So we have z modulo n, which I mean, sure, this is just the, what was it first, left, the zeroth left derivative of tensor product. So it should be the tensor product. Okay, bye Liam. So that shouldn't be that surprising. The more interesting question is, what is the first homology group? And again, it's the kernel of now this map divided by the image of this map. So it is, well, z modulo n divided by 0. So again, z modulo n. So this shows that, well, tensoring with z modulo n has torsion. Or I guess z modulo n has torsion, which, duh. Oh, and also hi is 0 for I bigger than or equal to 2. Yeah, don't know. Okay, so now this Tor in itself, okay, it has applications in whatever the universal coefficient theorem. Big deal, I guess. But it also helps us to, or like based on Tor, we can then define what's called group homology and Lie algebra homology, as opposed to the, I guess, a bit more useful group cohomology and Lie algebra cohomology. But first, let's do the homology. So let G be a group and M a representation of G. Then we can define the ith homology group homology group to be Tor I over the ring ZG of Z and M. So now we are dealing with the non-commutative group algebra with coefficients just in Z. Since M is a representation of G, we can sort of naturally turn it into a ZG module. And just by taking the trivial action, we can also turn Z into a ZG module. And then sort of the torsion tells us, I don't know, some global properties of the group. Yeah, according to Wikipedia, it doesn't have much of a an intuitive meaning. But for group cohomology and Lie algebra cohomology, there exist actual interpretations, which are much more interesting. Yeah, similarly, let G be a Lie algebra and over a ring R, and M or I guess a field R, K, and M a representation. Then we can define Lie algebra homology again to be the Tor I, R, and M, and now over the ring of the universal enveloping algebra of G. Again, sort of by trivial action, we can turn K into a UG module, and since M is a representation of G, we can extend that representation to be a UG module. Oh yeah, this is called group homology. And this is called Lie algebra homology. Yeah, I even wrote in my lecture notes, no idea what these mean. But the corresponding cohomology theories we're going to explore in a bit of time have a more concrete meaning. So now for the sort of more interesting functor, for the more interesting example of a derived functor, let A and B be R modules. Then we can look at the Yoneda functor. Namely the functor that maps some object C to Hom A C, I suppose, is left exact. And then we can right differentiate it. And so we can define what's called Ext. AB, yeah, now with an upstairs I to be the ith right derivative of HA applied to B. Now, I've already said that injective resolutions are just a pain to work with. And well, we would need to do that here. And we really don't want to. So we can leverage, well, what essentially amounts to the symmetry that we had for the the torsion functor to characterize Ext using projective resolutions. And that would be in form of a proposition. Equivalently, we can look at the functor HB, which goes from R mod opposite to R mod. And this one is also left exact. And then we have to take an injective resolution in the opposite category of R modules, which means that we have a projective resolution that is then turned into a cochain complex. If P2, P1, P0, A to 0 is a projective resolution.
Is the first word here equivalent?
Yeah, equivalently. Then this, if this is a projective resolution, then when we apply HB to it, we sort of have to reverse everything. Then we can again clip off the A part. and then have this thing. And this thing is again a cochain complex. With hi of that thing is equal to xi a b. So the fact that sort of the Hom functor is contravariant in one argument is what saves the day here, so that we can again work with projective resolutions. Yeah, and then I guess again we have some nice properties. We have a nice behavior with respect to direct sums, except that now this thing is sort of contravariant in the first argument. So co-products are turned into products. And in the second argument, products are turned into products. Yeah, the reason why we've already seen these is because, well, if you're talking strictly about modules of a ring, then we can define the depth of, what was it, the lowest index such that the ext is non-zero or something, compared to the height, which is the highest index such that the ext is non-zero, and when the height is equal to the depth for whatever the ring and the module.
So the sum turns into the product,
yeah,
and the product in the second turns into the product.
Yeah.
Okay.
Reason is that, like Hom, ext is sort of contravariant in the first argument and covariant in the second argument. So it's, yeah, then actually, again, like a functor defined on R module opposite Cartesian product with R modules. But yeah, like co-product is turned into product in the first argument, and in the second product is turned into product.
Would you mind filling out the hi of ... because it's a little bit different than in the left exacts.
Cochain complex 0 to HB,
Okay.
B naught to...
Okay, thanks.
Now, what can we use this for, apart from defining what a Cohen-Macaulay module or ring is? And we can use them to define, well, firstly, there is also a version of the universal coefficients theorem for cohomology theories, which then uses ext instead of Tor, but whatever. But more importantly, we can use it to define group cohomology and Lie algebra cohomology. So let G be a group and M a, well, we could say, oh, okay, well, G module, no. Oh, I guess it also has to be a group itself, okay. G module. Then we can define this thing to be the ext n. Yeah, again, basically a very similar definition, only instead of Tor, we are now using ext. This is the nth group cohomology group. Oh, and now I have this whole long part about what these mean. But I'm going to define Lie algebra cohomology first. Let G be a Lie algebra and a G module. Then HM GM is defined as, well, the Ext N over UG of Z and M. Is this correct? No, of course not. Well, it's a Lie algebra over C, and then UG is a C algebra, and then we have to take C there. And now I have long things about the interpretation of the zeroth, the first, and the second cohomology group of either of those theories. Which one would you like to hear?
Come again.
So I now have sort of long derivations of what the zeroth, the first, and the second cohomology group of these theories are. I guess, roughly speaking, the first one is, okay, for Lie algebras is actually more interesting. So the first one is some sort of crossed homomorphism. The second one, the zeroth, the first one classifies derivations, and the second one classifies central extensions in a way, and the same for groups. Which ones would you like to hear or see worked out in more detail?
I would prefer the first one because I don't know anything about Lie algebra, but do what you want.
Okay, so first one. Well, in any case, if we want to work those out, we first need to find resolutions. So I guess this is where we start in any case. First find resolution. So well, yeah, we want to do it by doing by finding projective resolutions. So we sort of start on the right. Now the first thing we can do is, well, Z is generated by 1, so we can really generate it by just one copy of ZG. Where we just map, what is it, any element G and G is just mapped to 1. Now the kernel of this map is, well, generated by sort of differences of two elements in G. And one way we can achieve this is by doing Z adjoint G cross G, which I think is just ZG tensored over Z with ZG. Is a free module because you can just take a basis defined by, or like in bijection to the elements of G. Well, in any case, it's a free ZG module, and you map a pair GH in G squared just to H minus G. And in a similar way, we can now take g to the third. And then do something similar. We take triplet GHK and map it to HK minus GH plus, okay, that is, I think that should be GK here, plus GH. And again, you can sort of verify that this indeed is an exact sequence and sort of carry on with higher powers of G there. There's a whole nice way of how to define these things. Basically by just taking a sum over all indices and then omitting that one and then taking minus I to that power, but never mind. So this works. You just have to sort of recursively go on there. And when we then apply the hom to that, we get 0 to, okay, the z thing, we throw that away. So then we have hom from zg to m. Now oh, did I write them wrong? I don't know. And so on. And what do these maps do now? Well, D1 of phi is now supposed to take a sort of linear combination of pairs of elements of G. So it takes one pair GH to phi of H minus G. And similarly, I guess D2 of phi takes a triplet GHK, and we'll just plugs whatever we defined above in there. So we have phi of HK minus GK plus GH. Or I guess, since we're talking about linear maps or Z linear maps, can write it like that, HK minus phi of GK plus phi of HK. No, GH, thanks. So now we describe the kernel and the image. Phi lies in the kernel of D2. Then we have, well, lies in the kernel of that thing. Did I write stuff wrong? Ah, no. Yeah, this means just that this expression is 0. So it means that phi AB is equal to phi CB minus phi CA. Or conversely, that phi of AC is equal to phi AB plus phi BC. And I guess, is Karthik still here? Yes. This looks a lot like what we used to call a co-cycle in I guess, topology in physics, when we took the co-cycle point of view for vector bundles and for principal bundles and stuff like that, just written now for an abelian group.
Ah,
just
like the transition functions you mean, or like you mean the for transition functions, or what does phi stand for
the
here?
transition functions, yeah.
Ah, okay. I didn't see this coming, but yep.
And now this means if we take, for example, 1 and the product of AB, this means that phi of 1 and AB is equal to phi 1 and A plus phi A and AB. And okay, I didn't really say how we turn this Z adjoint G cross G into a G into a G module, but we basically act on every of those elements here. So the fact that those things are all morphisms now means that we can pull out a factor of G if it's sort of at the beginning of every of those things here. So this is now equal to A phi of 1 and B. And this also means that phi is completely determined because we can sort of always divide by its first argument. Phi is completely determined.
Is there a reason because why you write product and plus in the one thing?
Yeah, those are different things. So the thing M is a G module, which means M is an abelian group, which has a representation of G. So this is now the group operation within M, the abelian group operation. And this is the representation of A acting on phi of 1 and B.
Also, like what is the equivalent condition, like in topology physics, of phi in kernel of D square? Or
I'm sorry, what?
so here we have like phi is in kernel of like D square, right? Or D2. Yeah. What is the equivalent condition for the transition functions in like the topology physics we saw? Because there we just
no, that is exactly that thing. So we've said before that if phi is in the kernel of D2, we say that phi is a 2 co-cycle, which is exactly that condition here.
Ah, okay.
So we want to describe the homology groups. So we first describe the co-cycles and then the co-boundaries, and then we see what the quotient looks like.
Okay.
And well, now I'm basically saying that we can complete that such a co-cycle is completely determined by a map f of g, which is defined as f of 1 and g, where f is a map from g to m. And well, we can translate this co-cycle condition here into the condition that f of AB, the product AB, is equal to f of A plus A times f of B. And those maps are called crossed homomorphisms. because they are sort of group homomorphisms relative to some sort of representation. We can turn them into actual group homomorphisms by saying that the group action should just be trivial if M is AZG module by just GM is equal to M, then this just reads f of a b is equal to f of a plus f of b, where, well, we're sort of working in a generically non-abelian group and in an abelian group, so we're using different symbols for the group operation, but like, yeah, it's a group homomorphism. And, well, those are the two co-cycles. But what are the two co-boundaries? So if phi is in the image of D1, then this means that phi of 1 and G is just equal to phi what? Okay, it's equal to psi of G minus 1 for some psi from ZG to M. Which is then equal to psi of G minus psi of 1, which is then equal to G times psi of 1 minus psi of 1. So that one is uniquely determined by some element of M. Which is just psi of 1. So this shows that H1 of GM classifies those crossed homomorphisms, maps F from G to M, such that f of AB is equal to f of A plus AF of B modulo, well, the trivial crossed homomorphisms that are of the shape f of A is equal to AM minus M for M and M. So I guess now it's already getting kind of late, but if you want more examples, you can look at the lecture notes and especially also at the document second cohomology, where I derive exactly in what way the second group cohomology group and the second Lie algebra cohomology group classifies central extensions, meaning diagrams of the shape 0 to M to E to G for our fixed G and our fixed M. So what can this E be? And it turns out that this E is some weird kind of co-cycle product, which we can define by or via the second cohomology group. And yeah, I guess similar for Lie algebras. Apart from that, we will see each other again, I believe, on Tuesday.